Welcome to the lecture. In the last lecture, we had discussed some graphical tools for diagnosing the violation of assumptions of the linear regression model. Now, continuing on the same lines, he will discuss here another violation of assumption. In any linear regression model, we assume that all the random errors epsilon 1, epsilon 2, epsilon n, they are normally distributed. And suppose we want to test this assumption. Now, what is the problem? The problem is that you are assuming the normal distribution for the entire population. And we have got here only a small data set on xi and yi. So, we would like to verify this assumption using some graphical procedure, and we have to use only the data on xi and yi's, whatever are available to us. Okay. So, this can be done using the normal probability plot, and this is also called as QQ plot. QQ plot means quantile plot. So, in this case, what we do is the following, that in the first step we fit a model and we obtain the residuals. In the second step, we try to order these residuals, and we denote them something like epsilon hat and 1, 2, 3, 4 up to n inside a square bracket. And the meaning of this thing is that this is the minimum value among all epsilon 1, epsilon 2, epsilon n, and this is the second largest value, and similarly this is the maximum value between epsilon 1, epsilon 2, epsilon n. So, these are essentially our ordered residuals. Then in the third step, we try to find out the cumulative probability. And the cumulative probability for the ith observation, this is computed by this expression I minus 1 over 2 divided by here n. I goes from here 1 to n. I would like to inform you here that as some softwares may use some other value instead of 1 by 2. So, that may be I minus something divided by n, right. But our basic idea is to compute the cumulative probability. Now, then we try to plot the ordered residuals versus pi, that is the cumulative probability. And when we try to do so, we can have different types of situations. And before we try to describe those situations, let me try to explain you the concept of heavy tail distribution, light tail distribution, positively skewed and negatively skewed distribution. Suppose I try to draw this normal distribution here. Suppose this is our normal distribution. Now, if there is other distribution whose tails are fatter than the normal distribution and the curve is like this, means all other properties like symmetry and everything is maintained. So, you can see here that this distribution has a tail which is heavier than the tails of normal distribution, and so this is called as heavy or say fat tailed distribution. And similarly, if I try to take here another distribution whose tails are thinner or lighter than the tails of the normal distribution, then this is called as thin or say light tailed distribution. And similarly, on the other hand, if I try to draw here a normal curve which is here symmetric, and suppose there is another curve which is more scattered on the left hand side, something like this. So this is our normal distribution which is symmetric around mean, and this is called as positively skewed distribution. And similarly, if I have got a curve which is more say scattered on the right hand side, something like this, so this is called as negatively skewed distribution. So using the QQ plot, we can identify whether the observations are coming from a distribution which is a heavy tail distribution, light tail distribution, or normal distribution. And also we can find out whether the parent distribution is positively skewed, negatively skewed, or it is symmetric. So I have plotted here say here 5 figures, and I would like to explain you that how we are going to interpret these things. So here you can see with this blue dots, I am plotting the observations between ordered residuals, say epsilon hat I, and say cumulative probability pi. And with the red line, I am trying to denote that what is the fitted line. So now, depending on the scatteredness of blue points around the fitted line, we can make different types of conclusions. For example, here in this case, in the case of figure number here 1, we can see here that the points are lying approximately on the straight line. So this implies that there is no problem and the underlying distribution is normal. Or in simple words, the observation which we have got y1, y2, yn from a normal distribution, right? And similarly, when we come to here figure number here 2, we can see here that there is a sharp upward and downward curves at both extremes. You can see here that on this extreme there is this sharp trend, and here this another sharp trend. So this implies that the observations are coming from a distribution which has got a heavy tails, or observation are coming from a heavy tailed distribution, right? Now, similarly in the figure number here 3, one can observe that the curve is flattening on extremes. How you can see here that, for example, if you try to observe over here, the curve is really flattening, and this implies that the observations are coming from a light tailed distribution. Now in this figure number 4, we can observe that all the points here are initially lying close to the straight line, and suddenly from the mid there is a sharp change in this direction. So one can observe here that there is a sharp change in the trend from mid, and this indicates that the observations are coming from a distribution which is positively skewed. And similarly in this figure number here 5, one can observe that the points are initially lying on us close to the straight line, and suddenly there is a sharp change in the trend from the mid, but in the downward direction. Okay, so here in this case there is a sharp change in the trend from mid in the downward direction. So this implies that the observations are coming from a distribution which is negatively skewed. Okay, so now from these figures, one can conclude about the parent population, whether it is normal or say heavily tailed or say light tailed, or it is a positively skewed population or a negatively skewed population. Okay. And these figures can be plotted using any statistical software, and they are available just by a click. One thing again I would like to emphasize that in these cases one needs some experience and practice to correctly infer from the plot about the parent population distribution. But there are some thumb rules that if I try to take the sample size which is more than 30 or 32, this produces a plots which are, I would call, better behaved. And if I try to take here n equal to 20 observation, this usually produces a stable plot. But if you have number of observation is smaller than 20, then it is difficult to obtain a good statistical plot. Okay, so this was all about the normality of the distribution. Now we come on the last assumption, and we would try to see how to verify it. So one of the basic assumption what we had made, that rank of x is equal to k. This means all x1, x2, xk, they are independent. Right. One option is to check whether they are independent or not, is to use the multiple scatter diagram that we had discussed in the earlier lecture when we were trying to plot the multiple scatter diagram between y, x1 and x2 in a linear regression model with two independent variables. So in case if we are getting a random pattern among all x1, x2, x3, x4 pairwise, then that would indicate that they are independent. And this type of situations can arise in practice. For example, if somebody is considering say the three variables, say income, expenditure, and say saving. So he or she might be taking them as x1, x2, x3, but if you try to observe, there is a relationship that x1 is equal to x2 plus x3, and in this case we have a problem, and this problem is called as multicollinearity. Right. This multicollinearity problem is one of the problem which has not got a satisfactory solution up to now, but there are different techniques which are available, and they can help us in diagnosing the problem of multicollinearity in the data. So one of the popular diagnostic to test about multicollinearity is to use the variance inflation factors. Right, and they are briefly denoted as say VIF. So this VIF for jth explanatory variable is defined as like VIFJ is equal to 1 over 1 minus R square J, where R square J is the coefficient of determination when the jth explanatory variable xj is regressed over remaining k minus 1 explanatory variable. right? J goes from 1 to k. So now this variance inflation factor, they are easily available in any software outcome, and they are the part of a outcome of a regression analysis, and they have the following interpretation, that if we are getting a variance inflation factor which is equal to 1, this indicates that the explanatory variables are not correlated. In case if we are getting a value of variance inflation factor between 1 and 5, this indicates that the variables are moderately correlated. And if we are getting the value of variance inflation factor, say more than 5 or 10, this indicates that the explanatory variables are highly correlated. And similarly, there are some other popular diagnostics which are like as condition index and condition numbers, right? So in order to find out the condition index, what we try to do here, that we consider the matrix X transpose X, and then we try to find out the eigenvalues of X transpose X. And suppose these eigenvalues or characteristic roots, they turns out to be the lambda 1, lambda 2 here, lambda k, right? Then based on that, we define the condition index for jth explanatory variable Cj is equal to lambda maximum upon lambda j, and j goes from 1 to here k, and where lambda maximum is the maximum value among lambda 1, lambda 2, lambda k. And similarly, we define the condition number as say here Cn, which is equal to lambda maximum over lambda minimum, where lambda minimum is the minimum value among lambda 1, lambda 2, lambda k. Okay, now how to interpret it? You can see here that this condition index is lying between 0 and infinity, and so this condition number and condition index, they have got a similar interpretation. So we can conclude that if condition number is coming out to be less than 100, then this would be indicating that the explanatory variables are are not correlated, or they are correlated very little, and in this case we can call that we have non-harmful multicollinearity in the problem. Similarly, if condition number is lying between 100 or say 1000, this possibly indicates that the explanatory variables are moderately correlated, and in this case there is moderate to severe multicollinearity. And if condition number is greater than 1000, this possibly indicates that there is a severe multicollinearity. Now again, I would like to say that these guidelines or these numbers, they are only indicative, and they are not something like a very hard and fast rule. So now we have finished all the diagnostic tests, whatever we can do in this in the given time frame. And now in the next lecture, I will try to emphasize on the use of software, and after that we will come on the forecasting. Till then, goodbye.